Welcome to HMA 431 Further Mathematics. This presentation will discuss one of the techniques in solving first-order differential equations, which is separation of variables. At the end of this video presentation, the trainee should be able to do the following: find the general solution of separable differential equations, and solve for the particular solution of separable differential equations. Let us recall first some of the basic differentiation and integration rules. The derivative of ax to the n equals a times n times x to the n minus 1. The derivative of sine ax equals a times cosine ax. The derivative of cosine ax equals negative a times sine ax. The derivative of e to the ax equals a times e to the ax. The integral of ax to the n dx equals ax to the n plus 1 over n plus 1 plus c, where n is not equal to negative 1 and c is an arbitrary constant. The integral of sine ax dx equals negative 1 over a times cosine ax plus c. The integral of cosine ax dx equals 1 over a times sine ax plus c. The integral of e to the ax dx equals 1 over a times e to the ax plus c. The integral of 1 over x dx equals ln of x plus c. A first-order differential equation of the form dy over dx equals f of x times g of y is called a separable equation. Let us consider example 1. Find the general solution of dy over dx equals negative 5y plus 3. Observe that this differential equation takes the form of dy over dx equals f of x times g of y. Our f of x here is equal to 1 and our g of y equals negative 5y plus 3. Thus, this is a separable equation. As a result of cross multiplication, negative 5y plus 3 and dx can simply be interchanged. Thus, we get dy over negative 5y plus 3 equals dx. Observe that the left side is expressed in terms of y alone and the right side is in terms of x. Hence, the variables are already separated. In this case, we can now integrate each side. The integral of dy over negative 5y plus 3 can be evaluated using integration by substitution. Let u be equal to negative 5y plus 3. Then du equals negative 5 dy. Dividing each side by negative 5, we get negative 1 over 5 du equals dy. Replacing dy by negative 1 over 5 du and negative 5y plus 3 by u, and introducing this negative 1 over 5 before the integral sign, we get negative 1 over 5 times the integral of du over u equals x. The integral of du over u is simply ln of u. Thus, we get negative 1 over 5 ln of u plus c equals x. Now, replacing the u here by negative 5y plus 3, we get x equals negative 1 over 5 ln of negative 5y plus 3 plus c. Applying some properties of logarithms, you can derive other forms of this general solution. You can just check our handout for some other forms of this general solution. This completes our solution for example 1. Let us now proceed to example 2. Find the general solution of d theta over dt equals 5 e to the 4t over e to the 3 theta cosine e to the 3 theta. Observe that this is also a separable equation. Cross multiplying, we get e to the 3 theta cosine e to the 3 theta d theta equals 5 e to the 4t dt. Observe that in this equation, the variables are already separated. Hence, we can now integrate each side. The integral of e to the 3 theta cosine e to the 3 theta d theta can be evaluated using integration by substitution. If you let u be equal to e to the 3 theta, then du equals 3e to the 3 theta d theta. Dividing each side by 3, we get 1/3 du equals e to the 3 theta d theta. Now this e to the 3 theta d theta can be replaced by 1/3 du since we have this equation. And e to the 3 theta can be replaced by u. And introducing this 1/3 before the integral sign, we get 1/3 times the integral of cosine u du. The integral of cosine u du is simply sine u. The integral of 5e to the 4t dt equals 5 times 1/4 e to the 4t plus c. Hence we get 1/3 sine u equals 5 times 1/4 e to the 4t plus c. Now replacing this u by e to the 3 theta, we get 1/3 sine e to the 3 theta equals 5/4 e to the 4t plus c. This is now our general solution. This completes our solution for example 2. Let us now proceed to example 3. Find a particular solution to dr over ds equals s cubed times the square root of s to the 4th plus 4 over r to the 4th, given that r equals 0 when s equals 0. Cross multiplying this, we get r to the 4th dr equals s cubed times the square root of s to the 4th plus 4 ds. Observe here that the variables are already separated, so we can now integrate each side. The integral of r to the 4th dr equals the integral of s cubed times the square root of s to the 4th plus 4 ds. This integral can be evaluated using integration by substitution. Let u be equal to s to the 4th plus 4, then du equals 4s cubed ds. Dividing each side by 4, we get 1/4 du equals s cubed ds. Now this s cubed ds can be replaced by 1/4 du, and this square root of s to the 4th plus 4 can be replaced by square root of u. Introducing this 1/4 before the integral sign, we get 1/4 times the integral of the square root of u du. The integral of r to the 4th dr equals r exponent 4 plus 1 over 4 plus 1 plus c. The square root of u is simply equal to u exponent 1/2. The integral of u exponent 1/2 du equals u exponent 1/2 plus 1 over 1/2 plus 1. Thus, we get r to the 5th power over 5 plus c equals 1/4 times u exponent 3/2 over 3/2. Simplifying this, we get our general solution. Substitute r equals 0 and s equals 0 to this general solution gives us c equals 4/3. Now replacing this c by 4/3 will give us this particular solution. This is our particular solution. 1/5 r to the 5th power plus 4/3 equals 1 over 6 times the quantity s to the 4th plus 4 raised to 3/2. This completes our solution for example 3. As an assessment, you are expected to complete the exercises provided in your handout. And this is on page 4. Okay, these two items can be found in your handout on page 9. Thank you very much.